Applications of double integrals. Give you some terminology. Lamina, a planar region, let's call it a very thin plate or a thin sheet is called a lamina. Think of it as being actually a sheet that actually has no thickness to it. And so it's a theoretical sort of sheet. It's a sheet of thickness, of no thickness, that's just in 2 dimensions. Even though it's a 3-dimensional object, it's in 3 dimensions, but it's a 2-dimensional object in 3 dimensions. So it's like a sheet of paper, but it has no thickness to it. But it will have other properties. So it's sort of a theoretical, it's idealized. So density, we will denote the density of maybe this lamina as rho xy. And the units are mass per area. So if I want to determine the mass, then I would just take the integral over the region D of rho of xy. That's if I want to figure out the mass of some region D having density rho. Similarly, we can think of charge. So it'll be the same sort of definition. So the charge will denote it by Q of some lamina D having charge density rho. Is Q is equal to the double integral over D of sigma, did I say rho? Of sigma xy, where sigma is the charge density with the following units: charge per unit area. Moments. So let me give you definitions of moments. Yes, I am going to give you first, second moments. Okay, so let me give you first the first moment. The moment about the x-axis is denoted by m sub x. It's just the double integral over d of y rho. The moment about the y-axis of the lamina D is m sub y, which is a double integral over d of x rho. Lamina D having density rho, I should have said. The center of mass for a lamina D having density rho is a ordered pair x bar comma y bar, where x bar is the moment about the y-axis, m sub y over m, the mass, is just m sub x over m. So instead of just plugging these in, we can say, well, the center of mass has coordinates x bar, the double integral over d of x rho divided by the double integral over d of rho, y bar, the double integral over d of y rho divided by the double integral of d over d of rho. The second moment. There are more than, well, there's, do I give the third moment? Kurtosis? Oh, I do give the third moment. Okay, so I do give some other moments. So the second moment. The moment of inertia. The moment of inertia about the x-axis, I sub x, is for the lamina D having density rho is I sub x, double integral over D, y squared rho. Moment of inertia about the y-axis, I sub y, is equal to double integral over D of x squared rho. The moment of inertia about the origin, I sub 0, is the double integral over D of x squared plus y squared times rho. The radius of gyration of a lamina about an axis is, well, let's define m r squared as I sub 0. Which means that m y squared, y double squared, is I sub x, m x double squared is I sub y. Parallel axis theorem. Let an object have mass m and line L sub m through the center of mass x sub m, y sub m, with moment of inertia I sub m about L sub m, then L is parallel to L sub m if the moment of inertia I about L is L sub I sub m plus d squared m, where d is the distance between the lines L and L sub m. Probability. So I'll be telling you some more about moments when they involve probability. A probability density function f. F is a probability density function if f is greater than or equal to 0 for all points. If the integral of f everywhere, the integral of f over Rn is 1. We define the probability as follows. The probability that a point is in lamina D is just the double integral over D of f, where f is your probability density function. We say that x and y are independent random variables if the probability of x, y is just the probability of x times the probability of y. If we have that the probability density function f of x, y can be written as the product of two separate probability density functions, f of, well, let's say f1 of x times f2 of x. In other words, if the probability of x and y is the same as the probability of x times the probability of y. Expected value. The mean, sometimes called the expected value, is the first moment. And so The mean with respect to the random variable x is just the double integral of x f of x, f x times f. The mean with respect to the random variable y is just the integral of y times f. The variance is just the second moment. It is, well, sigma of x squared. That's the notation. Oh, mu is the notation for the mean, and sigma squared is the notation for the variance. So sigma square of x is the double integral of x minus mu sub x quantity squared times f. Sigma squared of y integral of y minus mu sub y quantity squared times the probability density function f. The skewness is just the third standardized moment. And so my skewness, let's say sub x, so gamma sub x, is just the integral of x minus mu over sigma sub x minus mu such sigma over x minus mu sub x over sigma sub x, which is sometimes we call it z cubed, gamma sub y is the integral of y minus mu sub y over sigma sub y cubed. Again, it's just z cubed. The standardized random variable for y cubed, of y cubed. The kurtosis is the fourth standardized moment. So the kurtosis of the random variable x is just the integral of x minus mu sub x over sigma sub x to the fourth. The kurtosis of the random variable y is just the integral of y minus mu sub y over sigma sub y quantity to the fourth. So let's do some examples. Let's say on page 1064. I guess I'll need some room here to do this problem. So let me put in an extra page. So let's put in one more page here, at least. In exercises 3 through 10, find the mass, center of mass of the lamina that occupies the region D and has given density function rho. Okay, so problem number 6. D is a triangular region enclosed by the lines y equals 0. So let me draw this. So x, y. So y is equal to 0. So here's y equals 0. Y equal 2x. Y equals 0. Y equal 2x. X plus 2y equals 1. Okay. So my region D. Actually, let's try a little bit bigger. Okay. Something like this. Okay, so good enough. Okay, so this is my region D. Okay. So obviously this is 0 here. And when y is 0, x is 1. So this is 1 here. Let's figure out this. And so to figure out that, let's set these equal. Y is equal to 2x. So x plus 2y, but y is 2x, is 1. So I have 4, 5x is 1. So x is equal to 1/5. Let's figure out y. Well, plug in x equaling 1/5, so y equals 2/5. And so at 1/5, this isn't exactly the scale, but at 1/5, I'm here at 2/5. Okay. Okay. Oh, let's do a little bit more room here. So I want to find the mass. And again, I guess the density here is x. Maybe I should write where the density rho is equal to x. Okay. So I can either integrate over x. If I integrate over x, which looks perfectly fine, I have to actually split this into 2 regions. But if I integrate with respect to y, I only need 1 region. So let's integrate with respect to y. Y just because it makes it a little bit easier to integrate that way. And so let's switch this. So I have x is equal to y divided by 2. And here I have x is equal to 1 minus 2y. Okay. And so I can find the mass. The mass will just equal the integral over this region D. Maybe I'll just write it this way. The integral over the region D of rho d of a. And so the mass is, again, let's integrate with respect to y. Okay. And so, there it is, finally. So we're going from 0 to 2/5. So I'm just going from 0 to 2/5 here. And I'm going to integrate. By the way, rho is just x. And I'm going to do a dx dy. And so x here goes from this outer one, which is the 2y, to the inner one, which is the y over 2. So I'm going to, maybe I should write a little integration thing. So that's where I'm integrating over. Okay. Oops. D. So that's what I'm integrating over. Okay. So y over 2. Okay. So let's integrate this. And so the integral is just 1/2 of x is just 1/2 x squared evaluated between x equal y over 2 and x equal 1 minus 2y dy. What's the function we're integrating here? It's just rho. So we're just integrating rho. If you remember, here's the formula right here. The mass is just the mass of a lamina D having density rho is just the double integral over the lamina D of rho. Okay, that's the definition of mass. It's the density. All you're doing is integrating to find. So you have some region D here, defined its mass. Well, at every point here, it has some density, and so you would just say, well, if it had a uniform density, then the mass would be density times area. Now, of course, if it's not uniform, then you just integrate over your region. And so that's your answer. Okay. Yes, yes. Because that's what the problem says. Because it says rho of xy is equal to x. That was given. It has the given density function rho, and that was given in the problem. So that's part of the problem that we're dealing with. Okay. Obviously, it'd be different for every problem. Okay, so this is equal to. So let's just plug this in. 0 to 2/5. And so it's going to be 1/2 times 1 minus 2y squared minus 1/2 y over 2 squared dy. Okay, so this is equal to. Let's simplify this. So this will be 1/2 times 1 minus, so plus, well, 1 times minus 2y times 2 is a minus 4y times 1/2 is minus 2y. Plus 2y, negative 2y quantity squared is 4y squared times 1/2 is 2y squared. Y over 2 quantity squared is, well, 1/4 y squared times 1/2 is 1/8 y squared. Combine like terms. So the mass is equal to, and it goes 0 to 2/5. Actually, I probably could have integrated this just as easy without actually multiplying this out. So I actually could have just integrated this without multiplying it out, but let's do that since I already started it. So 2 minus 1/8, 16 over 8 minus 1 over 8 is 15 over 8 y squared minus 2y plus 1/2. Okay. So now let's just integrate this. And so this is equal to 15 over 8 divided by 3 is 5 over 8 y cubed. Oh, the 2's cancel, so you get y squared plus 1/2 y between 0 and 2/5. So 0 gives you nothing. So m is equal to 5 over 8 times 2 over 5 cubed. So the 2's cancel. The 2 cubed and the 8 cancels, and one of the 5's will cancel. And then this is a 2 over 5 squared plus 1/2 2 over 5. And then the rest of them gives you 0, of course. So let me simplify this. And so the mass is equal to so the 8's cancel, so you get 1 over 25 minus 4 over 25 the 2's cancel. Let's write this over 25. So that's 5 over 25, which becomes 2 over 25. So my mass is 2 over 25. So that's the first part. Now to do the second part, first let's find the moments. The first moments. A lot of times we just say the moment rather than call it the first moment. So to find the center of mass, well, actually, maybe I should say that. I didn't say I wanted to find the mass, but oh, maybe I'll just, nah. Okay, so now let's find the center of mass. So first, let's find the moments. Once I found the moments, all I have to do is divide by the mass. So let's do the center, let's do the moment about the x-axis. So this is just the integral. Maybe I'll call it d of y times rho. And maybe I'll call it, there, I'll use that notation. Okay, so let's do that first. And so this is equal to, well, d still looks the same. And so I'm not going to really change anything about that. So the moment was the integral from 0 to 2/5 from y over 2 to 1 minus 2y of y times x. Well, I'll call it xy. dx dy. So the only difference that I've done so far is I just put a y here. And it's the same thing. So let's integrate this. So this is equal to integral from 0 to 2/5 of, well, I have a constant y times the variable x. So the integral of the variable x is 1/2 x squared times the constant y. And I'm integrating between x equal y over 2 to x equaling 1 minus 2y. Okay, so this is equal to integral 0 to 2/5. Plug in 1 minus 2y. So this is 1/2 1 minus 2y squared times y minus 1/2, plug in y over 2, squared times y dy. Okay, so this is equal to integral 0 to 2/5. So I have here a 1 minus, so let's multiply out the 1 minus 2y quantity squared. So it'll give me a 1 minus 4y plus 4y quantity squared. Multiply a half y inside that. So I get 1/2 y minus, so that's a 4. So that becomes a 2. And that's a y times a y is y squared. Okay. Plus, last term is a 4y squared times a half is a 2y squared times y is y cubed plus 2y cubed minus that's a 4th, so that's 1/8 y cubed. Okay, so let's simplify that. Oh, everything else looks the same. So this is equal to integral 0 to 2/5 of 16 over 8 minus 1 over 8 is 15 over 8 y cubed minus 2y squared plus 1/2 y, which is actually the same thing we got from before. I'm just multiplying it by y, an extra power of y. Okay, so let's integrate this. So m sub x is equal to, divide by 4. So that's going to be 15 over 32 y to the fourth minus 2/3, now these are nice, y cubed, plus 1/4 y squared. We're going to get a lot of fractions over integral from 0 to 2/5. Okay, so plug in 2 over 5 to the power 4 minus 2/3, 2 over 5 cubed, plus 1/4, 2 over 5 squared, minus 0. Okay, is equal to, well then, let me put this down one. It's not gonna make it any shorter, so at least it'll make it easier to read. Okay, so now let's insert another page. So this is equal to, okay, so let's see. One of the 5's cancel, so you get a 3. So you get a 5 cubed in the bottom, and let's see, 2 to the 4th, 16, so you get a 2 times 5 cubed, and so that'll be 250 minus. Nothing's going to cancel there. So that'll be 2 times 8 is 16. 125 times 3 is 5. Oh, the 4's will cancel, so you get 1 over 25. And so the common denominator is 50. So 9 plus 30. So I have 9 over 750 plus 30 over 750 is 39 over 750 minus 32 over 750 is 7 over 750. Okay. Okay, good. Now let's do the other moment. So that's part of it. Okay, so I just need one more moment here. So the moment about the y-axis. Moment about the y-axis. So let's do that. So m sub y is equal to, and maybe I'll give it in this form, the double integral over d of y rho. Now it's going to be the exact same integral from before. So just like from before, it's the integral from 0 to 2/5. Oh, wait, 1 second. Doing about the y-axis. I have an error here. I have an error. I wrote it wrong, didn't I? Zero, sorry about that. The moment around about the y-axis. I wrote the formula wrong because we already did that. So it's the integral from 0 to 2/5. The integral, okay, come on. 2/5. Integral from y over 2 to 1 minus 2y of, well, in this case, it's going to be x times x. So this will actually just be an x squared dx dy. And so this is equal to integral from 0 to 2/5. Integral of x squared is 1/3 x cubed between x equaling y over 2 and x equaling 1 minus 2y dy. So let's evaluate this. I'm going to have to insert another page. And so this is equal to integral 0 to 2/5 of 1/3 1 minus 2y cubed minus 1/3 y over 2 cubed dy. Just plugging in your limits of integration. So this is equal to cube this. So this is 1 times, okay, let's do the integral. Zero to 2/5. 1 cubed is just 1 times a third is 1/3 minus 3 times 1 squared times 2y. So 3 times 1/3, so those cancel, times 2y plus 3, which cancels the 1/3, times 1 squared, times 1 times 2y quantity squared, so that's a 4y squared, minus 2y cubed times 1/3 gives you why don't I not do this? I'm just not gonna do this. I'm not gonna simplify this. It's a cube and it's just too big of a pain. Let's just not do this. I did them on all the other ones. I don't want to do this. Minus 3 cubed is 8 or 24 y cubed. Let's just leave it like this. And let's integrate. So m sub y is equal to 1/3 So integrating this, you're going to get 1/4. Then I have to divide by the derivative of 1 minus 2y, which is a negative 1/2, times 1 minus 2y to the 4th. So you can see that that's actually a correct integration. You could have done this by substitution, or, well, just sort of guess it like what I did. So if you take the derivative of this guy, well, you bring down the 4, so that cancels that, to the power of 1 less, so that's what's inside to the 3rd. And the derivative of what's inside, which is the minus 2, which cancels with that guy. So you just have this 1/3 and the 1 minus 2y to the 3rd remaining. Minus, let's integrate. And so the integral of y to the 3rd is 1/4 y to the 4th. So 4 times 24 is 96 y to the 4th. So this is 1 over 96 y to the 4th. And let's use these instead. And I'm going to evaluate between 0 and 2/5. Okay, so let's do that. So let's plug in 2/5 and 0. So m sub y is equal to minus 1 over 24, 3 times 4 times 2, times 1 minus 2 times, plug in 2/5 to the 4th, minus 1 over 96, 2/5 to the 4th. Plug in 0, so you get a minus, and the minus become a plus. 1 minus 2 times 0 is just 1 to the 4th. And then plug in 0, you get. So let me simplify this further. So I have m sub y is equal to negative 1 over 24. 1 minus 4/5 is 1/5. 1/5 to the 4th is 1 over 625. Minus 2 to the 4th is 16. 96 divided by 16 is 6. Times 5 to the 4th is 1 over 625. Plus, well, 1 over 24 times 1 is 1 over 24. Let me factor out 1 over 24 times 625. And so this is equal to a negative 1 minus 4 times 6, 24. 625 times 24 is 625 times 24. So this is equal to the moment around the y-axis is, well, 625 minus 4 minus 1 is 620. I can divide 620 by 20. So let me do that. 620 divided by 20 is 31. I'll write 20 as 4 times 5. 24 divided by 4 is 6. 625 divided by 5 is 125 times 6 is 750. And so now let's figure out the center of mass. Which is just equal to x bar, y bar, which is the moment about y-axis over the mass m, the moment about the x-axis, divided by the mass m. So this is equal to 31 over 750 divided by, we have a little bit more space here, the mass is 2 over 25. Uh, 7 over 750 divided by the mass 2 over 25. And so this is equal to 720 divided by 25 is 30 times 2 is 60. 750 divided by 25 is 30 times 2 is 60. So 7 over 60. And so we have the following center of mass. Let me do problem number 18. Find the moments of inertia, I sub x, I sub y, I sub o, the origin, for the lamina of exercise 6. Oh, so it's the same thing. D is the triangular region enclosed by the lines y equals 0, y equals 2x, x plus 2y equals 1, and rho is equal to x. So let's find first I sub x. This will just be the integral over the region D of y squared rho. So this is equal to, maybe I'll give one more line. Just as before, 0 to 2/5. It's the same region. Y over 2, 1 minus 2y. And now it's a y squared times x. So x, y squared, dx, dy. So this is equal to integral 0 to 2/5 of, well, let's integrate. So the integral of x is just going to be 1/2 x squared times the constant y squared from x equaling y over 2 to x equaling 1 minus 2y. And so this is equal to integral 0 to 2/5 of 1/2 1 minus 2y squared times y squared minus 1/2, plug in y over 2, y over 2 squared times y squared dy. So this is equal to integral from 0 to 2/5 of, let's square that. So it's 1 square times y squared times 1/2. So it's a 1/2 y squared, 4y to the 4th, 2y to the 4th, plus 4y squared, 2y squared times y squared is y to the 4th. Sorry, the middle term was wrong because it's a minus 4y. The 2's cancel, then multiply by y squared. Sorry about that. Plus, minus, 2 squared is 4 times 2 is 8, 1/8 y to the 4th dy. So this is equal to integral from 0 to 2/5 of y to the 4th. So that's 16 minus 1 is 15 over 8 y to the 4. That looks familiar. Minus 2y cubed plus 1/2 y squared. And now let's integrate this. Okay. And so if I integrate that, this is going to equal 1/5 of this. And so this is 3/8 y to the 5th minus 2/4, so 1/2 y to the 4th plus 2/3 y cubed, integrated between 0 and 2/5. Okay. Let's insert another new page. And so this is equal to 3 times 2 is 6. Good, I caught that. Okay, 3 times 2 is 6. Ooh. Okay, so let's plug in 2/5. So this is 3/8 times 2 over 5 to the 5 minus 1/2 2 over 5 to the 4 plus 1/6, 2 over 5 to the 3rd, and then everything else is going to be 0 when you plug in 0. So I sub x is equal to 2 to the 5th divided by 8 is 4 times 3 is 12. Okay. 5 to the 5th, that's a big number. That's 5 to the 5th, I think. No, it's not. Isn't it? No. Isn't it? Yeah, it is. 5 to the 5th is 31/25. Okay. Minus 2 to the fourth divided by 2 is 8 over 625, which is 40, okay, over 3125. But let's just leave it as 8 over 625. Plus, oh, you have to put a 3 in there. 2 cubed is 8, and the 6 I can cancel out a 2, so that'll be a 4 in the top. 3 times 125 is 375. So this is equal to. Let's multiply. So let's multiply by 9375. Okay, so that's 36 minus 4120 plus yes, 375. That's 25, so that's 100. So that's 16. So this is equal to 16 over 9375. 18. So yesterday I found this moment of inertia. Now I want to find the moment of inertia. Let me see if that says anything. I want to find the moment of inertia about y. And so I'll do x squared times rho. And so rho, if you recall, was just x. And the triangular region was the same that we've been using in the past two problems. So it's just the integral from 0 to 2/5 from y over 2 to 1 minus 2y. And so the integral of x cubed is 1/4 x to the fourth. And we're going to evaluate at the end points. So let me plug in minus 2y, subtract from it x equal y over 2. Well, y to the fourth is just y to the fourth. 2 to the fourth is 16 times 4 is 64, so 1 over 64. Now, let's integrate this. And so, I have here 1/4. Let's add 1 to 4 to get 5. So that's how I get my 5s here. And then, since this is not y, but 1 minus 2y, have to divide by its derivative, minus 2. And so I get 4 times 5 times 2 is 40. I plug in 2/5. I plug and then plug in 2/5. 5 times 64 is 320. Subtract from it, plugging in 0. And so if I plug in 0, this is just 1 to the 5th. 1 minus 4/5 is 1/5. 5 to the 5th is 3125. 2 to the 5th is 32. 320 divided by 32 is 10. 5 to the 5th is 3125 times 10 is 31 250. And then 1 over 40 times 1 is just 1 over 40. Let's factor out a 40 and a 3125. And so that just becomes minus 1 here. This becomes, well, you need a 4, so minus 4. And here you need a 3125. Minus 5 is 3120 over 40 times 3125. And so the 10s cancel. 312 divided by 4 is 78 over the 3125. And lastly, let's find the moment of inertia about the origin. Note that the moment of inertia about the origin can be found by using the fact that the sum of the previous two should give me the of the moment of inertia about x plus a moment of inertia about y gives me the moment of inertia about the origin. Or if you actually want to do it out, the moment of inertia about the origin is just the integral over d of x squared plus y squared times rho, the density. Again, rho is just x, so let's multiply x inside the parentheses. So that's an x cubed plus xy squared. And I'm integrating over that triangular region, the same triangular region. Integral from 0 to 2/5, integral from y over 2 to 1 minus 2y. Integrate x cubed, so you get 1/4 x to the 4th. Integrate x, so you get 1/2 x squared times your constant y squared. And you evaluate it in points y over 2 to 1 minus 2y. So let's plug in 1 minus 2y, 4th, plus 1/2. Plug in for x, 1 minus 2y squared times y squared. Minus, now let's plug in y over 2. So 1/4 y over 2 to the 4th. And then I'm subtracting, so minus 1/2 y over 2 squared times y squared. And so let's simplify. So I'll just rewrite the 1/4 1 minus 2y to the 4th because I can integrate this easily. Let's multiply this out because it's not as easy to integrate. So I get 1/2 times 1 squared times y squared is 1/2 y squared. I get 1/2 times negative 4y times y squared is negative 2y cubed plus 4y squared times 1/2 times y squared is 2y to the 4th, 1 over 64 y to the 4th minus 1 over 8 y to the 4th. And so you get 128 minus 8 minus 1 is 119 over 64 y to the 4th. And so let's evaluate this. So just like before, if I integrate this, I'm going to have to bring down, I'm going to have to multiply by 1/5 and 1 over negative 2. And so it'll give me a negative 1 over 40, 1 minus 2y to the 5th, plus 3 times 2 is 6, so 1/6 y to the 3rd, minus 2 divided by 4 is 1/2 y to the 4th, plus 5 times 64 is 320, so 119 over 320 y to the 5th. And let's evaluate between 2/5 and 0. So let's plug in 2/5. 1 minus 4/5 is 1/5. 5 to the 5th is 31/25. 5 cubed is 125. 2 cubed is 8. 2 to the 4th is 16. 5 to the 4th is 625. 2 to the 5th is 32. 5 to the 5th is 31/25. Plug in 0. Well, this will give you minus a negative 1 over 40. So plus 1 over 40 times 1 to the 5th. And all these other ones are 0. And so 40 times 31/25 is 125,000. I can cancel out 2 here. And so I get 4 over 3 times 125, 375. I can cancel out 2 here, so you get 8 over 625. I can cancel out 32 here, so you get 119 over 31, 31/25, 0, plus 1 over 40. And so you can add these up. And so you just get, and simplify, so you just get 2 over 75. But as I said at the beginning, and that's what you would expect, because if you added up the previous 2 examples, previous 2 calculations, you would get the same answer, 2 over 75. Okay, so let's go on to problem 28. Verify that f equaling 4xy if x is between 0 and 1 and y is between 0 and 1 and 0 otherwise is a joint probability density function. If x and y are random variables whose joint probability density function is the function f that we saw in part A, find the probability that x is greater than or equal to a half. 2, probability that x is greater than a half, y is less than or equal to a half. C, find the expected values of x and y. So let's do this. So let's show that this is a probability density function. To show this is a probability density function, I just want to show that if I integrate this everywhere, maybe I'll denote it this way, that I get that this should equal 1. Okay? Should equal 1. So let's show this. So let's integrate everywhere. Well, in this case, it's 0 outside of this unit cube, or unit square. So I'll just integrate inside the unit square. The integral of x is just going to be 1/2 x squared. So this is 2x squared. Y between x equaling 0 and x equaling 1. So nice calculation, nice easy calculation. Plug in x equaling 1, so you just get 2y. Plug in 0, you just get 0. So let's integrate this. And so if I integrate this, I just get y squared, the halves cancel. 1 minus 0. And so yes, it's equal to 1. I wanted to show is equal to 1, and I've just shown it. So maybe I'll just say done. Okay. Oh, and of course, there's actually one other thing. But that's sort of a trivial thing, but maybe I should write it down. And f is always greater than or equal to 0. So by definition, that was a trivial condition. Okay, so now it is a probability density function. So let's do part B. I guess part I. I want to find the probability. Well, that X is greater than or equal to 1/2. Okay, so let's do that. So this will just equal the integral. Let's go from 0 to 1, and from greater than 1/2 to 1 of my probability density function for x, y, and this is dy. Okay, so let's integrate this. So this is going to be the integral from 0 to 1 of 2x squared y between 1/2 and 1. And so this is equal to, and maybe I'll give it a more. Okay, so this is the integral 0 to 1. Plug in 1, so that's just 2 times 1 squared. Plug in 1/2, 2 times 1/2 squared dy. So this is equal to, go from 0 to 1 of 2y minus 1/2 y dy. And so this is just integral, it's from 0 to 1 of 3/2 y. So if I integrate that, I'm going to get, okay, I'm going to get 3/4 y squared between 0 and 1. So you plug in 1 and you get minus 0. So the probability x is greater than 1/2 is 3/4. Okay. Let's do part 2. So this is B part 2. So I want to find the probability that x is greater than 1/2 and y is less than 1/2. So let's integrate this. Oh, and of course, when I do the integration, I change my, they should be capital letters, but I like, for some reason, using lowercase letters. And that's just really an abuse of notation, but that's what I do. I like lowercase letters. Okay, so for y, it goes from 0 to 1/2. For x, it goes from 1/2 to 1 of my probability density function. So again, I should be using uppercase letters. So x dy. Let's integrate this. So this is equal to integral from 0 to 1/2 of 2x squared y between x equaling 1/2, x equaling 1. Plug in 1, so you just get 2y. Plug in 1/2, and so you get 2/4. same thing. And so I get 3/2 y. Let's integrate that. And so I get 3/4 y squared between 0 and 1/2. One half squared is 1/4 times 3/4 is 3/16 minus 0. And so I get that the probability x is greater than 1/2 and y is less than 1/2 is 3/16. Let's do part C. Part C, which says to find the expected value of x, the mean mu sub x. And so this is equal to the integral over r. Let's call it r2 of x f of x y dA. So this is equal to the integral from 0 to 1. It's for both of them, 0 to 1. Of 4x, so 4x squared y, dx dy. Let's integrate. Integral from 0 to 1 of 4/3 x cubed y between 0 and 1. So plugging in 1, I just get 4/3 y, and plugging in 0, you get 0. So let's integrate this. So this is equal to 2/3 y squared between 0 and 1. So if you plug in 1, you're just going to get 2/3. And so that's the expected value of x. Let's find the expected value of y. So this is just mu sub y, which is the integral over everything of y times f of xy. So this is the integral from 0 to 1 of 4xy times y, so 4xy squared dx dy. And so this is equal to integral 0 to 1, integrating x, I get a 2x squared y squared between x equaling 0, x equaling 1. And so if you plug in 1, you just get a 2y squared minus 0. So let's integral from 0 to 1 of 2y squared. And so if you integrate this, you get 2/3 y cubed between 0 and 1. So if I plug in a 1, I get that the expected value of the random variable y, again, I should use it as a capital letter here, is, well, 2/3 times 1 cubed minus 0. So it's 2/3. And so